So how to configure a matrix? There's basically 2 steps to it. One is to select the 2D array or arrays that you want to, and that'll determine your X and Z dimensions. So what we're representing here is sort of the volume that we're able to interface with. If you look at this number down here, smaller volumes out to larger volumes. Once you select your 2D array, then you can select the platform design, and the platform is what drives the Y dimension, the spacing between the 2D arrays. And it's interesting too, some people want very closely spaced arrays and they want redundant activity to show up on multiple sites. Others want as large a span as possible. They don't want any redundant activity across the array. So it depends on what your interests are. Here's some different designs just to show you sort of the space that's possible. This is a wide spaced array, only 2 shanks. This was for a researcher who wasn't really sure what the ideal depth would be, so we designed a probe that had sites at 4 different depths. This is a polytrode configuration. This is a really powerful technique for pulling signals out of the noise, or if you need to do spatial localization, you want to know where your neurons are or how they're connected to each other. So these closely spaced arrays, you can sample multiple neuron, or you can sample a neuron across multiple channels. Small sites, large sites. One of the things that people often associate with signal quality is the impedance of the electrode, and it's been a sort of naming scheme, or I don't know what the right word is, but a reference people have used since single channel microelectrodes. I need higher signal noise, so I want a higher impedance. Really what that translates to is your site size. So the impedance value per se doesn't give you a better signal amplitude. It's that the electrode size is smaller, so it's more localized in that electric field. You have a larger contact, you're going to get more averaging of that signal across that contact. We don't label our different probes as impedance. This is a low impedance, this is a high impedance. We look at site area. And what I learned, if you just look at these 2 examples, small electrode versus a large electrode. Small electrode will give you higher signal to noise ratios, initially. So those are recommended for short-term implants. They'll give you the best signal noise.
You're talking about action potentials.
Yeah, action potentials. Larger electrode sites tend to not give as high of a signal to noise ratio, but they tend to last longer. And I think that's because of the encapsulation process, tissue encapsulation, that it takes longer, to completely occlude a site from the neurons. So we typically recommend the larger sites if you're looking for long-term recordings. Some more designs, more options. You see the difference in shank spacings here. It's hard to see here, but these are 2 millimeters. These are 5 millimeters long. 5 millimeters. These are 10 millimeters long. So we've got a customer at Northwestern, Lee Miller, he's using an 8 millimeter probe, right? So he's an example of somebody who wanted to go down the bank of a sulcus and still target layer 5 in the cortex, but at 8 millimeters below the surface.
What's the maximum contact you can get on each probe?
Currently it's 32 per array, and that's a function of the cable coming off. That doesn't mean we couldn't extend that, but we haven't pursued that at this point.